Hey friends, welcome back to our YouTube channel Physics Zone. Today we are going to move ahead in our chapter of center of mass. In last lecture, we have discussed the center of mass for a body of two masses. Okay, the formula for that was x center of mass is equal to m1 x1 plus m2 x2 upon m1 plus m2. Okay, now if we have a lot of masses, means if we have a system of masses, then how will we find the center of mass? It will be nothing big deal. It will be like as x center of mass equal to m1 x1 plus m2 x2 plus m3 x3 and so on. Okay, now m1 plus m2 plus m3 and so on. Okay, now how can we write it? x, x center of mass equal to sigma I is equal to 1 to n mi xi upon sigma I is equal to 1 to n mi. Okay, this is the formula when the masses are in discrete form. Now we will find a formula when all the masses are in a continuous form. Okay, in that case, like as we have a body having continuous mass, now we will cut it into strips of small mass dm. A lot of small masses dm are contained in it, and then we will integrate it and find the center of mass. Okay, now what can we write for it? If we have to write center of mass for this will be as x center of mass equal to dm x1 plus dm x2 plus dm x3 and so on upon dm plus dm plus dm and so on, all the masses. Okay, now in form of integration we can write it as x center of mass equal to integral of dmx upon integral of dm. Okay, this is the formula for center of mass of a continuous mass distribution. Okay, now we will find center of mass for different bodies or different shapes. Okay, now first we will find the center of mass for a rod. Now we have a rod having continuous mass distribution. Now how will we find the center of mass for that rod? We have a rod having continuous mass distribution. Its origin is here. When we have to find the center of mass of a body, we have to consider a point on the body as origin. Okay, and then we will start finding center of mass. The length of this rod is L and mass of this rod is M. It is given. Okay. Now the formula for center of mass is integral of dmx upon integral of dm. Okay. Now what will be dm? This is the small part of rod of mass dm, and the length of the small part is, let's say, dx. As from moving here to here we have traveled distance x, so this small distance is the dx. Okay. Now we know linear mass density lambda is mass upon length. So for this small mass dm we can write lambda is equal to dm upon dx. Okay, so from here dm equal to lambda dx. So putting the value of dm here in the formula, we can write integral of lambda dx x upon integral of dm. As dm is integral of dm denotes that whole mass of the rod, and it is given that the whole mass of rod is capital M, so we can replace integral of dm by m. So it will be like as lambda is constant, so we can take here dx and this x dx. So x center of mass will be 1 by m. Value of lambda is m upon l, and integral of x dx is x square upon 2, and the limit of integral is from 0 to l. As the we are going from 0 to l, l is the total length, 0 to l. Okay, solving it we can write x center of mass equal to m to m cancel, so from here l, and putting value of x square as l square upon 2, l to l cancel, x center of mass will be l by 2. Okay, so center of mass for this rod is at half of l here. Okay, at distance l by 2. Now we will move ahead and find the center of mass for another shape. Let's find center of mass of ring. Think about where will be the center of mass of ring. You can imagine the point where whole mass of the ring is concentrated. We have this ring. This is its center. Its radius is r. It is angle theta. this is r. We are moving from here to here. This is angle theta. Sorry, this is d theta. Let's make it once again. This is center. We have considered it at origin. Okay, this is radius. This is d theta, and this is theta, and this is y. Okay, now formula for center of mass is x center of mass equal to integral of y dm upon integral of dm. Okay, x center of mass equal to integral of value of y will be, from trigonometry we can say it is theta, it is r, it is r. So this will be r sin theta. Okay, and what will be dm? We know dm is lambda dx. Here dx is this because dm is this small part. This small part is dm, so this will be dx. Okay, now what will be dx? Dx is the arc of the circle, and by the formula for the length of the arc of the circle we can write dx is equal to r r d theta. Okay, so dm will be lambda r d theta. Putting value here, lambda r d theta upon integral of dm represents here the total mass of the ring. So it is given that the total mass of the ring is capital M, so we will write here capital M. R square lambda will be constant, and integral of sin theta d theta upon capital M, it is equal to r square lambda will be, we know mass upon length, so mass is m upon pi r. 2 pi r is the circumference of circle, so it is 2 pi r. Okay, so putting value of lambda m upon 2 pi r, solving it we get minus cos theta. Integral of sin theta is minus cos theta, and limits are from 0 to 2 pi. As we are starting from here, we will move here and we will reach here again. We have covered an angle of 2 pi, so our limit will be 0 to 2 pi. Okay, 0 to 2 pi. Solving it we get here minus 1, cos 2 pi is 1, this minus sign will give here minus 1, minus cos 0 is 1, and this minus will make it positive, and 1 minus 1 plus 1 will give us 0. So x center of mass will be 0. Okay, like this we have found the center of mass for ring. This is 0. Now we will find center of mass for half ring. No change here, but little changes. In case of half ring, we have to cover half distance. Instead of covering angle 2 pi, we will cover here only angle pi. Okay, so our limit will change from 0 to 2 pi to 0 to pi. Okay, so only this part. We will consider only this upper part, not this down part. Okay, so we will move from here to here. Our angle will be 0 to 2 pi. So change it. Just change the limits and result will change. 0 to pi, 0 to pi. Cos pi is minus 1, and this minus sign will make it plus 1. Cos 0 is 1, and minus minus plus 1. So this 2 will cancel this r will cancel it, and m r upon pi. Okay, so our center of mass for half ring is, there is some problem, sorry, some mistake here. Let's see. The mistake we have made here is that we forgot the mass in denominator, and also one mistake is our lambda is m by 2 pi r, we have taken it, but it will be m by pi r because our ring is now half, and the circumference of half circle is pi r, so our lambda will be m upon pi r. Okay, so let's correct it. It will be pi r, it will be s r square m upon pi, and this m here, and it will give us 2. M to m cancel, r to 1 r cancel, it will be 2 r upon pi. Okay, so this is the center of mass for half ring. It will be like as, this is our half ring, this point is sorry, this is our half ring, and this point is somewhat here, from here. it is origin, means the center of mass is at a distance of 2r by pi from this origin. Okay, now we will find center of mass for disk. Okay, think where will be the center of mass for disk. Center of mass for ring is at center. Center of mass for half ring is at a distance of 2r by pi from the origin. Then where will be the center of mass for a disk? Think about it. We have this disk. Okay, this is our center. We know a disk is made up of a number of rings. We have this small ring, one more ring, one more ring. Joining a lot of rings, we will get a disk like this. Okay, joining a lot of rings one by one, we will get a disk. This is the disk. We have formed it by joining rings one by one. Okay, let's consider a ring inside this disk. Let's consider this ring. Let's consider this ring inside this disk. The width of this disk is dr and it is at a distance r. Okay, now the radius of this disk is capital R and the mass of this disk is capital M. Okay, what is the formula for center of mass? It is x center of mass is integral of dm x upon integral of dm. We know integral of dm will be replaced by m, so it will be 1 by m integral of what will be dm. Here dm will be, in case of ring we have material just on the circumference, but in case of disk the material is also inside, it is not only on the circumference, so we will consider here sigma instead of lambda. Okay, areal density will be considered here, that is sigma and dA. Sigma dA. dA will be the area of this ring. What will be the area of this ring? It will be 2 pi r dr. Okay, 2 pi r dr and sigma. What will be x? Means x center of mass. Here x will be x center of mass for this ring. We know x center mass or y center of mass all are at origin of the ring, so we can put here 0. Putting here 0 will make all things 0, So center of mass for disk will also be at origin 0. Okay. Now we will find center of mass for half disk. Let's consider it as half disk. Instead of this full disk, let's consider we have this half disk, just upper area. Now what will we change? X center of mass equal to integral of x is, what is x for half ring, 2r upon pi, and dm here is, here one thing we have to mind is here no 2 will not come because it is a half disk. For half disk it will come only pi r. So dm will be sigma pi r dr, okay, upon m. Now what is sigma to this r is small upon pi into pi and r square dr upon m. Sigma will be mass upon area pi r, 2 pi upon m. It will be r square by 2. We will move from 0 to capital R, solving it pi to pi cancel, m to m, 2 upon r, r square upon 2, r to r cancel, this to this. Sorry, we have made some mistake here. Here sigma will be mass upon area. Area is pi r square. Okay, half ring, so here pi r square upon 2. 2 will come here. So putting value m 2 upon pi r square, this pi to pi cancel, 2 upon m, integral will result into r cube by 3. We are going from 0 to radius r, m to m cancel. By solving it, 4 upon pi r square r cube upon 3, r square to cancel, it will give 4 r upon 3 pi. Okay, this is the center of mass for half ring. So it was all about center of mass for 3 shapes. We will move ahead in next lecture. Thank you for watching my video and have a nice day.